Good evening to everyone. Uh, Welcome to two weeks online workshop on energy simulation and CFD analysis in building. Today we are on day 7, so we are discussing the topic of year-round simulation. So today we are going to discuss year-round energy simulation in buildings. So today we are not going to discuss about the models. So we are going to discuss about the what are all the contents in the software. So from that we are going to discuss. Okay. So we have seen that in a software that there is an inheritance of the models. So the lowermost model we are going to have openings. Group of openings put together, it is going to become a surface. Okay. And group of surfaces. Okay, like in east, west, north, south, roof and floor. It will club together to form a zone, and number of zones put together, it will form a block. Number of blocks put together. Okay, already I told you block is like a floor. Okay, so number of blocks put together, so it will form building. Okay, so several buildings will put together, it will form a site. Okay, so this is the model in a instance. So we will be discussing the lowermost unit. So that is the opening, and we will be having nodes. So for all the nodes, we will be having the equations. We will be converting these equations into governing equations into linear algebraic equations, and then we will be using our computer to solve these problems. Yesterday we have seen that how we are generating the algebraic equations from the differential equation. So it is a one-dimensional equation. We are converting that into a tridiagonal three-term algebraic equation. So when I substitute it in the matrix form, okay, so it will be like a tridiagonal matrix. Okay, so and all these blocks like openings are linked with the surfaces. Surfaces are linked with the rooms or zones. Or zones are linked with the blocks. Okay, so blocks means floors. So all the floors are linked with the buildings. So that is how we have the model inheritance. Okay, and this is how we have. So this thing we have time and again we have discussed this. So these are the lowermost blocks. So okay, these are the windows. Okay, openings. Okay, so external wall, windows. So we can have even door also. Okay, so this group put together, it will form the wall. Okay, and walls, 4 walls, ceiling and floor put together, it will form a zone or room. Several rooms put together, it will form a block. Several blocks put together, it will form the building. Several buildings put together, it will form the site. Okay, so we can already we have seen that we can use the building energy simulation software for sizing of heating equipment, cooling equipment, and year-round thermal analysis. Even you can do the HVAC plant analysis. You can go for day lighting analysis. Even you can go for CFD analysis also. So that also we are going to discuss. Okay. So several, what are all the basic blocks of your building simulation software? So we will be having layout, activity, construction details, opening, lightings, HVAC, CFD. Okay. So I think this this also we have discussed already, and how an activity block will be. Okay. So all the activity block. So this is what I told: layout, activity, construction, opening, lighting, HVAC, generation, output, and CFD will be like this. So in each block, you have to go inside and you have to give the input. For example, for activity block, so here we have to go and give the input. So the room can be occupied for 24 hours, or it can be occupied for 12 hours, or it can be occupied for 8 hours. So this is depending on the schedule or activity template. So you can have a template. For example, if it is a school, you can have a template for that. Okay, so morning 9 to 4. Similarly, if it is a factory, okay, so similarly you can have 8 to 4. So if it is a 2-shift factory, again we can have a schedule. So that means the operation of the equipments in a premises. Okay, so it can be given in the form of schedules or templates. Okay, so this and all we have seen yesterday itself. We have seen you have to give the occupancy. You have to mention what are the holidays. Okay, so how much amount of energy consumed for district hot water heating, environmental control. So that is for heating, how much cooling, and we have to tell about the control. What is the heating set point temperature? You know what is set point temperature inside the conditioned room? What is the set point you are setting for a heater? Similarly, what is the set point you are setting for the air conditioner? Similarly, what is the humidity set point you are giving? RH, is it 50% or 60% or 40%? Similarly, you can set a set point for ventilation also. Okay, at wind and all, you can go for ventilation. Okay, so that means you can have a control for ventilation also. Door will open automatically when the temperature of outside goes down, and you can take the air inside automatically. Okay, so that means you can have a set point for ventilation also. Pressure, minimum pressure, and lighting, computer, office equipments. Okay, even catering and process. So why I'm telling again and again, because it has to register in your mind. Okay, so that's why I'm telling you these things again. And these are the inputs like in heat load calculation. So you will be giving all these things inside. Okay, what are all the loads which is entering, at what time it is entering, so that we will be entering. Similarly, we have to give the construction templates also. So after the activity, I have the construction template. In the construction template, I can have varieties of walls. So it can be an ordinary external exposed wall, it can be a below grade wall, it can be a flat roof, it can be a pitched roof. So you know that this and all you have studied, flat roof, pitched roof. Okay, so external exposed wall, okay, exposed floor. So like this, this you can have it. Okay, so this you can have it for. So all these templates are it is given. Okay, and for this also we are having desk templates. So they're telling inside you need not to go and give your material. You can very well go and give your material, but already it is there. If it is if the construction is made as per standards, so then you can go and give it is a medium weight flat roof. If it is a pitched roof, medium weight, or a pitched roof, light weight, like that you can give. Okay. So like that you can give the building details for the full building. So you can give for subsurfaces, internal thermal mass. Okay, so what is the heat capacity of the building, because it will determine how much heat will be stored inside the building. And component blocks also you can give it. Okay, surface convection, linear thermal bridging at the junctions, all the details you can give it in the construction. Okay, and similarly for the openings also. So openings means it can be a glass window. The window can be external window or it can be internal window. External window or internal. So the external window will be exposed to the sunlight. Okay, internal window it can be between rooms also. Okay, so the details, all the details we will be giving. And if it is a sloped roof of window, sometimes we give window in the roof. Okay, so that details we can give. If it is a door, if it is a vent means it is a opening. Okay, meant for fresh air. So all these details we can give it in the solve. Okay. So next is you can give the type of lighting also. Okay. So you can give the type of lighting. Okay. So whether what is the light? So here you can see it is a fluorescent light. Okay. So that spec is given, because you know lightings, there will be standards will be there. So all the specs you can give it inside. Similarly, you can mention it in terms of power density, how much watt per meter square of lighting you have taken, or you can give it in terms of luminaire. Okay, or what is the operation of the lighting? Okay, schedule for the lighting. Okay, so what is the return air fraction? What is the radiant fraction of the sun of the light? So light, whatever it is there, it can have two components. One is radiant fraction and a visible fraction. Radiant fraction will add heat to the room. So are we having a control for light? So that means we should have a sensor for lighting. And if external, if the light is there, okay, during daytime, so the intensity of the lighting inside the building, it can go down. So you can have a light sensor like a LADR. So after that you can it will sense the light. If the external light is there, okay, automatically it will reduce the intensity of inside the lighting. So that is lighting control system. Okay, so you can have a task and display lighting, external lighting. Task and display lighting, already I told it is a specific lighting for specific application. Okay, for example, for reading or for your presentation like this. So you can have specific type of lighting. Okay, and HVAC. In HVAC, you can talk about mechanical ventilation, how much ventilation you are going to give, and how much heating you are going to give. So you can give what is be the COP for the heating. Why we are writing COP for heating? Because we may use heat pump for heating. Okay, so in Western countries, mostly they will be using heat pumps for heating, because that will be most energy efficient. Because if you are using an electric heater, so 1 kilowatt of work given, it will give 1 kilowatt of heat. But if I'm going for a heat pump, so for 1 kilowatt of electrical work given, it will give 4 kilowatt, if the COP is 4. So that is how, okay, so you can give the spec of the equipments, okay, heating, similarly cooling, what type of system, okay, and the COP of the system, okay, seasonal COP of the system, so that also we are giving. And we are giving a humidity control, district hot water, natural ventilation. So this natural ventilation is different from a mechanical ventilation. Mechanical ventilation is through a fan. If you are taking outside air for the fresh air purpose, it is called mechanical ventilation. If you are having a control system for the window, and if you are whenever the outdoor temperature is going below, okay, below the set temperature, okay, so then you can use very well use outdoor air itself for cooling the building. Okay, so that sort of natural cooling, it is called as natural ventilation. So regarding earth tube, I told you. So earth tube, it is earthen heat exchangers, where when air is passed inside the tubes, okay, buried down in the earth, so the air will get cooled in the summer season, and it will be heated in the winter season. Okay. Okay, so all these details, okay, so air temperature distribution, so all these details, it can be given in the HVAC systems. Okay, so this we have seen. And the next thing what you have to do is there are component libraries. Okay, so for each component there is a library. Just now we have seen for construction there is a library, for glazing there is a library. Materials, okay, so for all the materials there is a library. What are the materials? Pans, okay, textures, window glass, local shading. Okay, so for that we have a component library. Even for blinds, in blinds itself we have different types of blinds. Okay, so we have a component library. So what you have to do, you have to just go inside and then you have to select the corresponding material. So that's what we got a library. Okay, library means you go inside, you select the component what you want. Okay, so that is what we call it as library of material. Okay. So winds, several types of winds are there. Schedules, different types of schedules are there. Just now I told you. So it can be a school building schedule, okay, educational building schedule, or it can be a industry schedule, or it can be a commercial schedule. It can be a hotel schedule for your hotel. Okay. Similarly, you can give holidays also. Okay, a library for holidays, and we can give profile, load profile. Okay, so all these things are available. Okay, so how it is available? So it is you can see it is available in this form. So you can go for a construction, glazing, holidays, hourly weather. So all this material, metabolic rate, even for metabolic rate also I told you. So the metabolic rate, it depends on the people, age of the people, depend on activities. Okay, it will have both sensible and latent. So that means for that also they are given a library. So that means you have to go inside and you have to select. Similarly, pan, profile, schedule, structure. So everything you have to go inside and just you have to select it. So that is called a component library. Also, we have something called as a template library. Okay. Okay. So let's see. So if I open one of this, okay. So for example, if I work construction, so inside that I'll be having, this is what I called as a library. So like it is like a buffet. So whenever you are going for some function, so if there is buffet, what you will do? So there will be a variety of food materials. So whatever you want, you will go and select. So like that only here. Okay. So here you are finding ceiling, door. In construction, you are having ceiling, door frames, floors. Okay, floor itself, you are having variety of. So, and even if you open this also, okay. So if you open this also, inside that you will be having a another list. Okay, so that is how you will be having. So even you can see, okay, for materials, if I open construction, I have like this. If I go for materials, I have these things. Okay, so materials, here I'll be having material property. Okay, so and okay, so here you can see, if inside the material, if I open, okay, there also I have, see, for example, if I'm opening the brick, inside the brick itself I have a variety of bricks. Okay, so I have AEC brick and aerated concrete block, brick outdoor with the dimension, smallest dimension, next dimension, next dimension. So brickwork, inner leaf, so concrete block, glass block. So all these things are available. So that means each folder will be having these libraries. Okay. So that means if you all the materials are available, you do not search for the material. So I would say that in your standard building simulation software, so you don't require data book. Okay, so for, what I do is whenever data is required, I just go inside and try to get the data from the building simulation software, because all the data will be there inside. Otherwise, you have to go and change, search everywhere in the. Okay, but now here all the data and even standards also it will be there. All the type of standards also it will be there. So that is what we call it as component library. Okay, so the next is template library. So I told you template library means you will be having templates for activities. Okay, so if it is an educational building, what is the template? Okay, so if it is a hotel building, what is the template? If it is a commercial building, what is the template? Construction templates, glazing templates. Okay, different types of glazings are there. Okay, and the factored templates are there. HVAC templates. Okay? For example, it can be a DX plant, it can be a variable air volume, or it can be a chiller. Okay, so it can be a radiant cooling system. So many templates are available. Okay, so location templates. So location templates, so many locations are there. Okay, so many the templates will be there for each location. So the weather stations will be there at selected locations in the world. So in all the places where you have the weather stations, the data will be available. So that is what we have. So similarly, if I am selecting some location, so that is called a location template. Okay, and you will be having hourly weather data templates, metabolic rate, pressure coefficients. Pressure coefficients means so you will be having factor. Okay, so you will be having factors for calculating the drag force. Okay, so that is called as the pressure coefficient. Okay, P by half rho c square. Okay, so that is called as pressure coefficient. So even cracks also, different variety of cracks may be there. So for that also we have a library. Legislative regions. So what are the energy codes followed? So each country will be following their own energy codes. So there also we have a library. And what are all the different types of sectors? Domestic sector, agriculture. I cannot say that. Building sector. Okay, so in the building, what are all the different sectors? Commercial sector, educational building sector. Okay, so hotel building sector. So like that you can have. So similarly, different time zones also. Okay, so each country will be following a time zone. So that means that the timing also we should know whenever we are going for simulation. So all these things are available. Okay, so it will be like this only. So the template libraries will be like this. If you go and open, it will be like this. So we'll be having a lot of folders. For example, I've taken construction templates. There's a lot of folders. So yearly design is over the practice. Okay, so in that itself, several things are there. So inside you can go and select. For example, here you can see best practice heavyweight, best practice lightweight, best practice medium. Okay, and this is one method of selecting. Okay, so otherwise you can have based on energy code heavyweight, lightweight, and medium. Okay, so that is how you can have different varieties. Okay, so if you go inside, for you'll be having a lot of templates. Okay, so but that is how you can get familiarized with the software. So if you know about how to work with the templates, so you can work with the software. So when I talk about all these things, okay, I will complete this discussion. So when I talk about all these things, there may be a question from your mind: is it possible for us to enter the properties of material in the building simulation software? Yes, it is possible. Okay, so there is a procedure for entering. Okay, you can go and copy one of the template, and after you can go inside, and after that you can change the properties. Okay, and you can create your own template. Like for example, if there is a two-layer bricks, and inside you have an insulation layer, or inside you have some other material. Okay, you yourself you can give that. Okay, so that means there is a possibility. Okay, maybe tomorrow I will explain about that, how to give a property. Okay, so how you give a property to a building simulation. Okay, from external we can give that. So it is very well possible you can give it. Okay, so that is how. So that means standards are also available. If you want to give the values also, it is also possible. Okay, so Okay, now from that we will go to the analysis. So yesterday we have taken this building, okay, atrium building, and this building, okay, so it had 2 floors, and we have an atrium which is not at all air conditioned. Uh, so now this we have considered for a simulation yesterday. So yesterday when I was speaking, there was some small mistakes in the simulations. So today I have corrected everything and I will present it. Okay. And we know this is the standard thing. So first what you have to do, so you have to create a new site. Okay, you have to tell what is the location to the building simulation software. And after that you have to create a new building. That means you have to draw the building. Okay, so and you have to mention various blocks. Okay, you have to see that the geometries are correctly mentioned. So you have to mention the partitions also correctly, because mostly in the building's outer walls it is easy to put. If you go inside, drawing the partition wall and giving a window door in the partition wall, so that will be involving. So that we have to do it properly. Okay. Similarly, any custom opening is there, so that the window doors and other things you can give it, and you can go for sizing of heating and cooling system. So that means you can calculate the heat load and the cooling load. Okay. So that we will be doing it for summer and winter. So based on the hourly data, so that we know that we did yesterday. And so if you have done that, if you have checked the model for this, then you can go for annual simulation. Okay. So okay, so this we have seen that. Okay. Okay. So when we are doing the calculation for the cooling design, okay, so it can be done based on the inside air temperature or inside operating temperature. So you know what is inside air temperature? Okay, the temperature inside the building. So or you can do it with the operative temperature. Operative temperature we have seen it is a combination of radiation and room temperature based on the convective heat transfer coefficient, weighted average convective heat transfer coefficient. So in that you can take a 0.5 radiant fraction. Okay, and from that you can do that. So it is possible for us to do that, and you can go for a design one. That means you can give a factor of safety. So usually you will be giving some extra cushion. So why we are giving that cushion? Because sometimes we'll be interested in pulling down the load immediately. So if you are giving an extra kilowatt, so that means it will the system will perform faster, and it will pull down the load very easily, very faster. Okay, especially in shops and all, they will be doing that, because once the shop is started, if it is taking more time for cooling, people will get uncomfortable. So that is why they will be giving some extra kilowatts or extra tonnage for that. Okay, so that we give this safety factor, we give it for cooling equipment as well as heating equipment. And sizing you can have it based on Ashray method or unitary DX when you are planning for unitary DX plant or VAV plant. Okay, so all these options are available. You can go inside and you can give it, and even in the solar options also. Okay, so you can include all the loads. Okay, selective loads, all the loads you can include, and even shadings also. If there is a shading from the surrounding, okay, there can be a tree or there can be a adjacent building. So shading can come from that adjacent building. So that will reduce the tonnage of your equipment. So that also you can do it. Okay. So now, okay. So these things, till this you should have discussed already. Now we are going for year-round simulation. Okay. So in year-round simulation, we can do a annual simulation. That means throughout the year, 365 days you can do it, or you can do it for a summer design week. That means the hottest week of the year you can do that. Okay, or summer. So or you can do it for summer typical week. Okay, so it is based on the weather data translator. Okay, so or you can do it all summer alone. So you may be interested. So it's all depend on. Okay, so all it is required. So very simple. You give the period, you will get the simulation. Okay, so all these things are just fancy names only. Okay, winter design weeks means it is a week on winter, and the typical week also. Okay, it is based on another transmitter. So all winter also you can do simulation. So that means simulation means you will be doing it over a period of time. Heating and the cooling calculation you will be doing it for one day only, for peak day only. Okay, so that you have to remember. So heating and cooling design you do it for peak day, and simulation you will be doing it over a period of time. It can be over 1 week, or it can be for 1 month, or it can be for 6 months, or it can be for 365 days also. Okay, So then only I'll be calling it as a simulation period. Okay. And whenever you are doing the simulation, so I told something about total time and the time steps. So for a building, when you are doing a simulation, so always the total time is fixed, that is 365 days. So if at all, if you want to for one year simulation, okay, and what will be the time step for hour if you are dividing it into two? So, okay, so that means for every half an hour, if you take delta t as the 30 minutes, okay, so that is one possibility you can do it, okay. And if you are going for non-HVAC simulation, so you have to go for 4 time steps per hour. Okay. And if it is for HVAC simulation, it is 6 time steps per hour is suggested. Okay. So that there is provision. You can go and you can select it. Okay. If you want more accuracy, you can increase this number. That I need not tell you. So you may be knowing. Already I told you if you want more accurate results, so the delta t should be reduced. Okay. So if you are reducing the delta t, the other problem is the number of calculations will be very much higher. If you are having a multi-storied building, that means a very big complex is there. Okay, like a mall, if it is there, and you are having all the components, and if you are going for a smaller time step, okay, then it will be a problem. So if you are having a small building like this atrium building, okay, just 2 floors alone, and if you are going for smaller time steps, there is no problem. You can calculate very easily because the number of nodes will be smaller, so you can calculate very easily. But if you are having a multi-storied building like Phoenix Mall or a very big mall, so that means a very big building. So all the parts you are taking, so that means the number of nodes will be very much higher. So in that, if you are going for, if you are reducing the delta t and you are running the calculation, so you will find that the capacity of your computer may not be sufficient. So the simulation will be running slow, number one. Number two is there may not be space for storing your results. So that problem will be there. So that is where you will be having problem. So there you will be problem in storing the results. So that means your computational capacity may not be sufficient. So that means there you have to go for stations, workstations. So if you want to do it for a very big buildings and all, okay, and if your time step is very much smaller, so it means that more number of nodes and lesser time step. Okay, you require a higher computational capacity. That means workstations are required. But if lesser number of nodes, even lesser time step also, it is not at all a problem. The easiest one should be if you are doing calculation per hour or per half an hour, and if you are having a smaller building, then you will get the result immediately. Okay, within 2 or 3 minutes, you will get like how I get it for this atrium building. So this and all it will be easy, but the same thing is not applicable for a multi-storied building. Okay, if you are doing simulation for a multi-storied building, it's not. Similarly, if you are taking the time step, if you are having a 1 second and all as a time step, so then it will take more time. Okay, so this you have to know because it is something to do with the computational capacity. That means your laptop or your workstation or your system, what you are using, so that should have sufficient capacity. So this is important for you. So that's why I'm telling. And the temperature, you can have a temperature control also. Okay, inside the room. Okay, so inside the room you can have a temperature control. So it can be controlled maybe based on air temperature or operative temperature. Just now we have seen like how we had it in a cooling design. Okay, so here also you can have the control. So you should know control is very important because suppose if you are keeping the room at maintaining the room at 25 degrees, so if and you are finding some energy, the same room if I am maintaining it at 15 degrees and if I am finding energy, the energy value it is going to increase. Okay, so that is why the set point is very important. Okay, so cooling set point or heating set point, it is very important. So corresponding energy value should be added. Okay, so that it should be added to the energy. So that is why I'm saying. Okay, so set point temperature is very important. Okay, now we will go to the analysis. So this is the model what we have taken yesterday. So yesterday we have did for Bintulu, Malaysia. So we know that it is at a 3 degree north latitude. and we have done the cooling calculation. Okay, since it is at the equator, so uh, so this is the cooling calculation. So the outdoor temperature, it is at maximum, it is going up to 32, not 32. It is going up to 34 degrees centigrade, 34 or 35 degrees centigrade. Okay, and we have calculated the load. Yesterday itself we have calculated the load. So the load was around 123.64, and then we have we calculated the heating. Okay, we know that the heating quantity is going to be less. So at the peak, I'm trying to find at the peak. So the value is 1.06, but still I am getting 0.0 only. Okay, so I'll tell you the reason. Because if I'm okay, so I'll go to the energy things and then I'll explain. So then I do the energy simulation. Okay, so I do the energy simulation. So I go and give the period. I give the period of simulation as 1 hour, and I am going for the simulation. Okay, so from this simulation you can see that these are all the things. So this is the district hot water gas. Okay, heating. Okay, so then this is the cooling spikes. This I think yesterday we have seen, and we have the lighting also. Lighting, it is almost constant. And the room electricity also, it is constant. And we are finding that these are all the schedules. Yesterday I told you. So this is office building. Okay, office building. So I have 2 days holiday. Okay, 2 days holiday. So every weekend 2 days will be holiday. After the weekend, we found the value is increasing. This value is increasing. That is energy for Monday, it is going to be higher, because 2 days, whatever the heat is there from the atmosphere, it will be stored in the building. So Monday morning, if you switch on the air conditioner, so first it has to clear that heat. Okay, so that means Monday morning it will work. The compressor will be working for a long time. So that is why this peak is there. Okay, this peak is there. And when you go for Tuesday morning, the same thing will not be there. Okay, so the cool down, the temperature would have been cooled down, and uh, the energy content will be lesser. Okay, so that is how. So every week up to weekend it will reduce, and the first day of the week it will be more. So that is what first we have to note it. Okay, and how about the energy consumption for the cooling? So that is for air conditioner. So it will be you will be finding it very strange throughout the year. You are finding it that it is same. It is almost the same throughout the year. It is almost the same. Why? Because it is near the equator. So because the equator, so you will find that the temperature will be between here itself. You can see this outside dry bulb temperature. It is given here. Okay, below it is coming only up to 25 or 24. Throughout the year, the lowest temperature is 24. Okay, and the highest temperature we have seen that. Okay, so highest temperature will be around 34 or uh, yeah, so 34 degrees centigrade. So that means what is happening? So only cooling will be required, no heating at all. Okay, so that is one you have to understand. And also the radiation received. Okay, so the radiation received, load, everything, it is almost uniform throughout the year. So that is what we are finding. So that means near the equator, this will be the load pattern, and the energy consumption, it will be like this one. Okay, it will be like this one. Something interesting to note. Okay, and these are the loads. Okay, so these are all the loads. Okay, so all these loads, okay, computer and other things. Okay, so that is given here. It is having a minimal value, and because of the load we have the energy consumption. So the energy consumption is given here. Okay, so it is almost like what we have discussed a single day. Okay, single day calculation. So we are getting it in the same way. So and above zero, whatever I have it, those are all the loads. Below zero, okay, so below zero, so what I have, okay, so that is the cooling energy. Okay, so that is the cooling energy. Okay, okay, so now what is happening is you can have mechanical ventilation and the natural ventilation. So those things it is available throughout the year. Okay, so that is also during working hour it is available. Okay, so that is what you're taking, and you're using it. Okay, okay, fine. So now uh, we are going for Chennai. Okay, so when Chennai it is at 13° north latitude. Okay, so then you know the peak temperature. Okay, so outside the dry bulb temperature, so it will go up to 40 degrees centigrade. Already I told you it will go up to 40 during peak day. Okay, so this is air is conditioned. Air is conditioned, and mind you, this is a, cooling design. Okay, so this is not energy simulation, and this is the radiant temperature. This is the operative temperature, and this is the cooling. Okay, so this is the uh, indoor temperature, indoor air temperature. Okay, and these are the loads. That's just now you have seen, no, load per day. Okay, so all the loads are it is given here for the daytime. Okay, for the daytime, what are the loads? So all this put together, so you will get a graph like this. Okay, here the top. The same thing it is given here. Okay, so the same thing it is given here. So this is the cooling. Okay, so this is the cooling load. Okay, and I have the total cooling is this much. Okay, sensible cooling is this much, and the difference between that represents the latent, and that latent will be following this pattern because you are taking outside air during daytime. You are taking outside air, so that means you have to cool the outside air. You have to bring down the latent load. So that means during daytime only this latent load, this band will be there. Okay, and this is a ventilation. Okay, so this is for Chennai, and this is the cooling load for the Chennai, and this is the heating load what we calculated for Chennai. So a small amount 8.82 is there. Okay, 8.82 is there, and for the zone 1 it is 8, and it is that is ground floor, it is 8 kilowatt, and first floor, okay, it is 7.83 kilowatt. Okay, so this is cooling. Some amount of cooling will be there at Chennai. Why? Because we are at 13° north latitude. Otherwise, that will not be there. If you are at the equator, this cooling heating load will not be there. Okay, and now you can see the difference. So this is energy simulation what you have done for Chennai. So you compare it with Bintulu condition. Okay, Bintulu Malaysia condition. So now here you can see your peaks are very much less here. You can see not very much less. So it is less in the month of January, and similarly December. Okay, so here you can see here it starts from January and in December. January, February up to March. Okay, so the cooling load is less, and the similarly after September the values are lesser, and in the month of May, June, August, this area. Okay, so I have greater than. Okay, so this you know. Okay, so because the sun will be traveling towards the north, and during this month. Okay, so up to it will go up to June equinox. Okay, up to June equinox, the sun will be traveling. So when sun is traveling, it will come, and then it will be retrieving. So after that, I'll be having maximum. And this sort of pattern. Okay, so you will not see it in Bintulu. Bintulu will not have this pattern. And in Chennai also, you can see the ambient temperature, because the ambient temperature is a representative of radiation. Okay, so here you can see during December it is coming up to 24, and slowly it is rising as the radiation is rising. Okay, so it is rising up to June, and then after that it is slowly it is decreasing. Okay, and it is going up to December. Okay, so until December it is reducing. So this is outdoor air temperature or outdoor dry bulb temperature. It is a representative of the radiation received, or it is a representative of the cooling required. Okay, just put this point in the mind. Subsequently, we are going to discuss this point again. See, outdoor air temperature, dry bulb temperature, it is the representative of the uh, radiation received, or it is the representative of the cooling quantity. Okay, so this point you just put it in your mind. We'll have a discussion afterwards. So what is that you are finding comparing the Bintulu, which is there at the equator, and Chennai? So in Chennai during December. Okay, so in the December. Okay, from January, February, March, up to March, and after September. Okay, there is a reduction. Okay, there is a reduction in the outdoor temperature. So cooling load reduced, but the cooling load increases. You can see the cooling load is increasing. Okay, because of the earth heating. Okay, cooling load increases up to June. Then again it decreases because of the solar. Okay, so these things you can study. Okay, so this thing you can study, and now you can you ask yourself whether I can how to do the loading calculation in April 10th, because April 10th is the sun overhead position for Chennai. But whether are you maximum temperature, outdoor temperature, where it is? It is not at that point. Maximum temperature is there at June only. Okay, so then you have to question yourself when I have to do the calculation. Okay, so wherever you are having maximum load, there only you have to do the calculation. So I think I hope and your loads will be maximum in this area only, the vicinity of June and July. Okay. Okay, fine. So many interesting things are there to note down. Okay, and you can see this is the cooling load. Okay, so it is increasing. Okay, and it is decreasing. Fine. Okay, so fine. So this is for Chennai. Okay, so next we will go to the Mumbai. Okay, Mumbai. Yesterday also we have seen about Mumbai, and Mumbai is 19-degree activity. We are at 13. Mumbai is at 19. Okay, so a small difference is there. So for that we are doing the cooling load calculation. So Mumbai, the peak temperature is not as high as Chennai. Okay, so but in cooling design, I have 36 or 37 degrees. Okay, that is the peak temperature, and we are calculating the loads. Okay, all the loads we are calculating as usual, and this is the total load. Okay, and the latent load. Okay, compared to Chennai, it is lesser, but the latent load is there because Mumbai is near the seashore. Okay, and okay. Now, what is happening? We are calculating the cooling load. Okay, so cooling load we are reduced so smaller extent, 104.82. You have to know that we are doing it for the same building. We are not changing the building. Okay, we are doing it for the same building. So then we are calculating the heating load. Okay, so the heating load it is coming 20.4. Okay, it is coming 20.4. And yeah, so for ground floor it is 18.43, and the floor one, first floor, it is 18.29. So as per the calculations. Okay, so these are all, I think this is not required. This is the outdoor condition for Mumbai. Okay, the ambient and the temperatures. It's a free floating temperature without any air condition. How the things will be. Okay, so that is what is given here. Now we will go here. Okay, so we will go to the load whatever we are having. So the cooling electricity, like Chennai, it is increasing. You can see it is increasing. Again, it is decreasing, almost like Chennai only. And even the temperature also, it is also almost like Chennai only. So minimum is 24, and maximum it is 34. Okay, maximum outdoor air temperature is 34. But for Chennai, you have up to 38 degree. Okay, up to 38 or 39. Okay, so up to that will go. And the pattern of a cooling load, it is following almost like Chennai only. Okay, so that is it. But just by looking, we cannot calculate the load. Load you have to do it by integration. So already I told you the load multiplied by time. It is so that will give me the energy. So that means I have to integrate this curves. Okay, so that is what. So usually the solvers it will do the numerical integration. So that's how you will be getting the energy values. Okay. So next we are going to Delhi. So now we are near 20. Mumbai we are near 20. So now we are going near 30. Okay, so that is Delhi, which is 28.7 north latitude. Okay, so then for Delhi we are calculating the cooling load. So the Delhi maximum temperature is 45 because it is interior and the radiation is more. Okay, so 45. So Delhi summer is hot. So then I have the loads and I have the cooling. Okay, so then during the night we are maintaining the humidity. Okay, during the daytime we are maintaining the humidity. Nighttime humidity is very less in Delhi. You can see that less than 35. Okay, so dry, it is dry. Okay, yeah. So we are calculating the cooling load. Okay, so we are calculating the 54.22 and 54.33, and we are calculating the heating load. So 60.36. So here you can see it is 54.22 and 54.43. Okay, for Delhi, so almost heating and cooling, it is you are getting the same value. Okay, for the design. So yesterday I think I had a few problems in getting the values. Okay, so now today I got the correct results. I am presenting the correct results. Small errors were there yesterday, so that I have eliminated now and I am presenting. Okay, so now you can see Delhi, there is a visible difference. Okay, there is a visible difference in the energy consumption pattern. So here you can see during the January, February, March, up to March. Okay, so no cooling, only heating is required. Okay, only heating is required. Okay, and after that cooling is required. Okay, up to maybe October, and after that heating is required. Okay, how I can understand that? See the outdoor temperature. Okay, so outdoor temperature, it is coming 10 degrees. Okay, so it is coming 10 degrees, okay, in the month of January, and even yeah, so in December also. So from 10 degrees it is increasing, unlike Mumbai and Chennai. So you are having 10 degrees here. So then outdoor air temperature is rising during the months June, July, it is maximum, and after then again with the uh, sun movement. Okay, so again the temperature is decreasing. So you can see the even the cooling energy requirement, it is increasing, and then it is decreasing. Okay, and then it is decreasing. Okay, so that is how I will be having the pattern. Okay, so in these portions you will be requiring heating. Okay, but the heating is not shown here. I will tell you the reason why it is not shown here. I will tell you the reason. So because something interesting I noted. Okay, so that I will share with you. And the next is we go to now we had at one discussion. Delhi is at near 30° north latitude. Then we are going to Barcelona's plain, because that is at 40° north latitude. So beyond that, in India we may not have a 40° north latitude. I don't think we don't have. You have it in China. So that's why I'm taking Barcelona, Spain. So for that I have done the analysis. Okay, so heating. Okay, so I have to do the heating. The heating value is higher. Okay, for Barcelona, Spain, it is natural. And yeah, so for the zone 1 ground floor, this is the value. For the first floor, this is the value. Okay, and I'm going for cooling. Okay, Spain, Barcelona, Spain, I'm going for cooling. So on the hottest day, the lowest temperature is 25 degrees centigrade. Okay, the highest temperature is 30, yeah, 30 or 32 degrees centigrade. Okay, so based on that we can do the load calculation. So the load calculation, okay, so the load calculation is 0. I think I worked out. Okay, so I have worked out in that table. I'll just show you. Okay, I had some value. Okay, I had some value, so it is there. Yeah, so then we are going for energy. Then we are going for energy for the Barcelona, Spain. And here you can see like Delhi only we are having the pattern. Okay, so minus this is 5 degrees. Okay, there it was 10 degrees. For Delhi it was 10 degrees. Okay, here you can see less than 5, 3 degrees and all we are getting during January. And here again November, December also we are getting the same pattern. Okay, so low temperatures are, and cooling is required only for few months. Okay, so only for 3 months cooling is required. Okay, so remaining time and all heating is required. Heating is required, and so it is similar to Delhi, but this cold region. Okay, cold region heating regions which require heating, so it is more, and the cooling region it is reduced, and again the heating requirement it is higher. So this is for Barcelona, Spain. Okay, so I think most of the patterns are very well known to you. So that is why I'm showing here. Okay, the maximum temperature of the outdoor air, it is only 25. Okay, so that means it is in the Joule. And again, whatever purposely I have taken everything in northern hemisphere just to know that the sun movement, because at this in this area the sun will be at the uh, December, okay, solstice. Okay, so this the sun will be in the December solstice, and at this spot it will be at the sun will be at the June solstice. That means the sun will be at the Tropic of Cancer. So that's why you are having some value here. Similarly, even for Delhi also, the value will be maximum here because of the sun will be at the Tropic of Cancer. So here it will be at the Capricorn. So that is why the values are lesser here. Okay. And the next we are going the extreme, that is 60.9 amount, that is Sweden. So for that we are doing the, so I am calculating the heat load. So then I am calculating the heat load is very much higher. Okay, so 182, so almost the value 163 and 164.72. Okay, the value is higher. And cooling load. Okay, so the cooling load, you can see that the maximum temperature is 25. Okay, maximum temperature on the design day. And some amount of cooling I have calculated. So based on whatever the solver is giving, so I have calculated. Okay, so again it is coming out to be 0. Okay, so I will okay, so I will tell you what is okay, so and I have the consolidated value. Okay, so that I will show you. And this is the energy simulation value, for Ammat. Okay, Sweden. So here you can see the temperature, how much it is going, outdoor temperature. It is going from -10, maximum it is only 20. Okay, so that is what is happening at Ammat, Sweden. Okay, the outdoor temperature is -10, so then it is going up to maximum of 21. So that means mostly heating only will be required throughout the year. Heating only will be required. So some portion, okay, some portion of the time cooling will be required. Okay. Okay, so since it outdoor temperature maximum it is 20, so we need not cool it. Okay, so that's why cooling load it can be 0. It can be 0. Okay, so that is what we have to understand. Okay, so when here also the same pattern only. During June solstice, I have radiation. Okay, so that is since it is in northern hemisphere, it has a maximum, but it is less only. Peak is less only. And this is during the December solstice. Okay, lowest value. Okay, what is that we are finding that heating period is extending. Okay, it is extending further. Okay, okay, so that is what we have. So now I have the consolidated table value for the energy simulation. Okay, so Bintulu, Malaysia, that is the 3-degree north latitude. The cooling load is 131.46, and the heating load it is 1.046. Okay, and the cooling energy is 26887, and the heating energy is 0. So we were wondering, see, we have got a load of 1.06. Why we are not getting a heating energy? Okay, so I was also having the same doubt. Okay, similarly for Chennai, heating load is 15.89. Here I am having nil. Similarly for Mumbai, I am having 36.72. Here I am having nil. So so after thinking, so we should know that this is an office building. So in the office building, the occupancy will be there only during the daytime. Nighttime there will not be occupancy. But our peak winter condition will be there at nighttime only. So that means at nighttime it is not going to work. Though I have this heat load of 1 for Bintulu, and for Chennai if it is 15.89, and for Mumbai if it is 36.72, night times it is not going to work. The building is not going to, because I have specified that as a office building. So it is going to work only during the daytime. So that means whenever cooling requirement is there, that only it will be working. Nighttime it will not working. So that is why 0 values are there. So next is when I come for Delhi. So here you can see the as I'm moving here, the cooling load is decreasing and the heating load is increasing. Okay, and when I come for Delhi, okay, so when you come for Delhi, and cooling energy is more, heating energy is less. So this may be contradictory. Whether I have equal, here I have equal contribution, but here this is not proportionate. The reason is again same, because of daytime only. So in Delhi also, so you are going to operate the building during daytime only. So that means only AC will be on during this. So nighttime you are not operating. Nighttime only cooling is required. So that time you are not operating the equipment. So during the daytime, heating requirement will be very much lesser only. Okay, so that is what we have to note. And after that, I am going to Barcelona's plane. There the heating load is more. Okay, so after that, again cooling energy only it is more. Okay, and the heating energy is somewhat higher. So again for the same reason, this also will be operated during daytime only. So because of the settings, we are getting a daytime cooling energy only. Okay, and So the same thing for armored Sweden also. Okay, so for armored Sweden also. So though you are having more heating load, okay, so it's due to daytime operation, cooling energy is higher. But when you compare to this, it is reducing. Okay, but this compared to this value is higher. Okay, so this value cooling energy in kilowatt hour it is higher. Okay, and the heating energy is lesser. Okay, so this is because of the operation. So then I was thinking, so for checking this, what I did is I converted this occupancy into resident occupancy. So when I converted, then the situation it changed completely. So that means I had more heating energy than cooling energy. So that is the thing. Okay, so that is the thing. So it depends on the occupancy. So here we should be careful. So suppose if you are going for a design, so based on this building, so if you are giving a 157.88 kilowatt heater or 327 heater for this building, so I think it will not be used throughout most of the time. Okay, because of the schedule of the building. Okay, because daytime operating schedule it cannot be used. Similarly, even in Delhi also. Okay, if you go for this, so this will not be operational. Just 1 minute. Somebody is with the. Please mute your mic. Aditya, the Aditya. Yeah. So that is the first, and this is what we have to understand. Okay. So if I go for 24 hours modeling or 24 hours simulation or 24 hours occupancy schedule. So if it is a residential building, then both will be same, and in fact this area will be very much higher compared to this. So now this is the problem. Okay, since we are going for this. Okay, since we are going for this uh, uh, daytime operations, we are having a thing. So that means only if you do the simulation you will understand all these things. Okay, so that is why simulation is very important. If you are a designer, just you go with whatever the basic design procedures, and it will you have to see what is the peak timing. Okay, whether the peak time is coming through for these two cases, it is coming during night time. But if you make the design based on that, your equipment working time is very much less, and even for Delhi also. So all these things you have to be noted. Okay. Okay. Next we will go to the energy consumption calculation. Okay. So how energy consumption to be calculated for air conditioning or a heating application. So most I should not say that some of us will be having a wrong notion that if you want the total energy, just the rate of equipment, that is power of the equipment multiplied by total time, you will be getting the power. So first you will be take let us take the Bintulu condition. Okay, so it is working out as 131.43, and I am multiplying that by 365 days and 24 hours. Okay, so now it will become kilowatt hours. So when I am finding that it is around yeah, so 11,51,326. So that is the thing what I have. But the actual energy consumption when we find out using the solver, okay. So how much I'm getting? It is 2,68,887 kilowatt hour. Okay. So why there is a difference? So the difference is because you are designing the equipment for a peak day. Okay, if that equipment will not be running throughout that time, so that we should understand, it will not be running throughout the year. It will run for some time, it will stop. If it is a very sunny day, or if loads are higher, it will operate for a longer time and stop. If the load is less, it will operate for a shorter time and it will stop. So that means energy consumption is not equal to equipment rate into total time. That is power of the equipment into total time. That is wrong. So energy consumption depends on the heat gain throughout the year. So that is what we have discussed during the load calculation also. So the heat gain throughout the year it is given by this one only, whatever we have calculated. So whatever the energy simulation you have, through the energy simulation you have calculated this kilowatt hour. So it means that through all these things, okay, so through all this, you are integrating everything, you are trying to find out. But if you are trying to take the total capacity, okay, if you are trying to take the total, this is the peak capacity. So if you take the peak capacity, it is like this value, peak value multiplied by the full year. So this will be a very big area. So that is what we are having here. But the actual energy consumption, it is less, this much only. This is not Pintulu condition. I'm telling you, even for Pintulu condition, you will be having like this only. Okay, but it is very much lesser. That is what we have to note. So that means actual working condition. So your compressor will be cutting off. Compressor will be cutting off often if it is a cooling equipment, and your heater will be cutting off if it is a heating equipment. So that means what is energy consumption? Energy consumption is either the area under the curve, what you have it in the energy simulation, year-round simulation. Okay, in the year-round simulation, what is the area under the curve? So that means energy value multiplied by the time. So integral value. So that should be the energy. Or for the same time only, equipment also will be running. So that is compressor will be running or heater will be running for the same time only. Okay, so that is why you are having. So that means the correct energy consumption is just equipment rate into compressor on time, or equipment rate into compressor off time. Okay, this is most important concept that we should understand. Or it is a very basic concept, but that we have to understand. Okay, so now if you try to consolidate, what is that you have to understand is when room temperature above the comfort temperature, cooling is required. When the room temperature is below the comfort temperature, heating is required, and cooling is proportional to outdoor temperature. Okay, above the comfort temperature. Similarly, heating is proportional to the outdoor temperature below the comfort temperature. Okay, so how you calculate the energy, heating, cooling rate into time for which the equipment is on. I think this slide we have discussed in the day 2, but again for reminding, I am bringing it here. Okay. Now from there, now this is the correct time to study about what is cooling degree days. So before today's discussion only, previously I told that the outdoor air temperature. Okay, so the outdoor air, the amount of cooling requirement is proportional to the building load, rate of heat gain. So the amount of cooling requirement, it is proportional to the rate of heat gain. Okay, so the amount of cooling load, it is proportional to the or amount of cooling required, it is proportional to the cooling load of the or the rate of heat gain. Okay, in other words, the amount of cooling load or the amount of cooling required is proportional to the outdoor temperature. Just now we have seen that during in the equator, so you have constant outdoor temperature. That is why cooling also it is almost constant. When I am coming to Delhi, so you are finding that not only Delhi, in Chennai, Mumbai and Delhi, we are finding that January, February, March and October, November and December. So you are finding the values are their load is not there. So that means there the ambient temperature, outer ambient temperatures are less. So that means the amount of energy required, I can say that it is proportional to the ambient temperature. Okay, that is one form of telling. Or we can say that we can have some reference line. Okay, so here you can see in this drawing a reference line of 20 degrees. So now whenever the temperature, ambient temperature is going above that temperature, then what is happening? Cooling is required. Or I can say that my cooling equipment will be working whenever the temperature is going beyond 20 degrees centigrade. So how much it is going beyond the 20 degrees centigrade, that much amount of energy, proportionate amount of energy will be required for cooling. How I can calculate how much it is going beyond? Just you can count the box. Okay, so you can see I can call that as cooling degree days. So what is cooling degree days? So it is a measurement designed to quantify the demand of energy for cooling. Okay, cooling degree day is derived from the measurement of outdoor temperature. Okay, it is cooling degree day. the cooling requirement of a building at a specific location are considered to be directly proportional to cooling degree D. So that is just now I explained. So if my outdoor temperature is more cooling is required, my compressor will be working for a long time. So that is what we have to understand. How much it is above this particular temperature, so much a cooling load will be. Okay, so that is how. Here you can see when it is 11 o'clock, you are seeing it is just it is at 25 degrees. Okay, so that means the compressor will run for a shorter time. But when I am going to 18 degrees, okay, I mean 18 hours. So the it is you can see at 10, 15 degrees above. So I can say 15 into corresponding hours. So for 1 hour, 15. So that means 15 degree hours. So here it is around 2 degree hours. Here it is 5 degree hours. Here it is 10 degree hours. Okay, so that is why for every hour, if I am calculating, I will be getting a degree hours. So here degree hour is less, 5 degree hours, 10 degree hours, 12 degree hours, 15 degree hours. So like that it is. So my degree hours are increasing. So now if I sum all these degree hours, okay, so I will be getting the flow rate of energy that is required for cooling. And I can divide that by 24. Okay, so then my cooling degree hours will become cooling degree days. So cooling degree days is proportional to the energy consumption of the cooling equipment. Similarly, if it is going below a particular temperature, okay, if the ambient temperature is going below a particular temperature, then there may be heating requirement. So that is obvious, we should understand. So it will be like this. So now here they have taken 14 degrees as the reference line. So if the temperature is going below, okay, 14 degrees, okay, so then heating requirement is there. So heating requirement is a measure of design to quantify the demand of energy needed to heat the building. Heating degree days is derived from the measurement of outdoor temperature. So how you are telling like outdoor temperature is if it is higher, cooling is required. If outdoor temperature is lower, heating will be required. Similar in same way, pro rata, proportional. Okay. So the heating requirement for a given building at a specific location are considered to be directly proportional to number of heating degree days at that location. So here you can see it is 14 degrees, but actually it is 7. Okay, so think that it is Barcelona. So 14 is the reference, but it is 7. So how much heating is required? So 14 minus 7 degree hours. Here it is 14 minus 6 degree hours. So like that 14 minus 5 degree hours. So like that I get the degree hours. I add all these degree hours, I will be getting this area. I divide it by 24. So then I will be getting degree days. Okay. So now the amount of heating required, it is proportional to the degree days. So similarly, amount of cooling required, it is proportional to the cooling degree day. Amount of heating required, it is proportional to the heating degree days. So now you should understand what is degree day. Now, if you think that if for a particular location, okay, so throughout the day, if the condition is moderate, it is almost 20 throughout the day. So that means what? That the building will not require any cooling requirement. Similarly, heating requirement also will not be there. So that means cooling degree day is 0. So for example, if it is cloudy, for example in Bangalore, if it is cloudy, okay, so then means throughout the day you may be having around 18 to 20 degrees. So that means you don't require a heating equipment, or you don't require a cooling equipment also. So that means no energy is required for cooling. So that is the significance. Please try to understand. Okay. So that means if outdoor temperature is very much higher, hottest summer, a cooling degree days cooling degree day will be higher. Coldest winter, heating degree day will be higher. So if the climate is very moderate, okay, pleasing and moderate climate is there, so these things will become 0. So that means what? So this cooling degree days and heating degree days indirectly tells you how much will be the amount of energy will be required for cooling or heating. Okay, fine. So next is now from here, from the map, you can you yourself you can tell where and all cooling degree days will be required and or will be there, and where heating degree days will be required. Very simple. Already we have seen this classification. between 20° north latitude and 20° south latitude. Okay, so here you will be requiring a I told that throughout the year it will be hot. Just now we have seen that it is a Bintulu condition. So throughout the year it will be hot. So that means throughout the year you will be requiring only cooling. No heating is required. So that means only cooling degree days will be there between the 23 and of north and the 23 and of south. Mostly only cooling degree day will be there. Okay, no heating degree day will be there. Okay, fine. So next I'm going between 20° north latitude and 40° north latitude. So there uh, it is like Delhi. Okay, it is like Delhi. So there cooling degree days also will be there. Heating degree days also will be there. During July and all, cooling degree days will be there because it will be very hot. You have seen that it is 40 degrees, going up to 40 degrees. So extreme cooling will be required. So cooling degree days will be there. During a winter, so it goes up to 10 degrees. So heating also it is required. So between 20° north latitude and 50° north, 40° north latitude, both cooling degree day and heating degree day will be there. Similarly here also 20° south and 40° south. Here cooling degree day and heating degree day will be there for Australia. So beyond 60° north, okay, only heating degree day will be there. Or okay, so 40 and 60, okay, 40 and 60. Again, this combination may be there. Cooling and heating degree day will be there, but cooling degree day will be lesser only. Okay, so here also 40 and 60, cooling degree day will be lesser. Heating degree day will be there. But beyond 60, only heating degree days will be there. Okay, so now just put it in mind. Everything you just put it in mind. Okay, this is, and world round the heating and cooling degree days it is given. So here you can see that when you are in the near 50° 60 degrees, heating degree days are more. Okay, compared to for Mongolia, Russia, Finland, and all. Okay, why? Because it is above 40° north latitude or 50° north latitude, around 50° north latitude. So here you can see heating degree days are higher compared to cooling degree days. And when you it is Thailand, Indonesia, and other things. Okay, so it is these things are in the equator, near the equator. Here you can find that cooling degree days are higher, and this thing heating degree days it's almost not there. It's not there. And China, you can see, China is like Delhi or closer to Delhi conditions. You will find that both are significant. Cooling degree day is also there, heating degree day is also. So they are both these things are. So you can see that it is typically between 20° north and 40° north latitude. Okay, so that is how you have to understand. Okay, so cooling degree day it is an important parameter. So cooling degree day it will tell you how much energy it will be required for heating your building. Okay, so you should not always think in a year. If you are having the equipment based this is very important concept that I have to tell you. So you can go for simulation and you can find what is the energy value, but that energy value will be not there in reality. The reason being some portion of the time there will be cloudy. Okay, there will be rain. So most of those things we will not be doing in the simulation. But if you want accuracy, you can include that and you can do it. But mostly we may not be doing it. For example, in Chennai, if it is a rainy season, it will be comfortable. Similarly, in Bangalore also, if it is a rainy season, it will be comfortable. So if you are going by energy simulation software, so the value what you are going to get, it is going to be higher because you are not going to accommodate this rainy season, comfortable season. So that at that point of time, they may not be using the AC and the heating equipment. But the energy simulation software, it will give that value. So what will happen? Your energy simulation will give you a higher value. In reality, you will be having a lesser value because during this comfortable season, you would have not used to your equipment, or your equipment will be working for a shorter period of time. The compressor will be working for a very shorter period of time. So that the difference will be there. That you have to understand. Okay. So that difference will be there that we have to understand. So that is dependent on degree day. If, for example, if for this Bangalore and Chennai, whatever I'm telling, if you are calculating the degree day throughout the year, then you will understand how much will be the energy requirement for this year. Okay, because degree day will be different for year after year. So in 1 year, if it is more cloudy throughout the year, okay, so then the degree days will be lesser. But 1 year there is no rain, no cloudiness, very hot summer is there in Chennai. So that means a cooling degree day will be very much higher. So there it is, a difference is there. Okay, please try to understand. So that means the real picture of energy consumption, so it will be given by the cooling degree day only. Okay, so that you have to take. So if the surrounding is comfortable, so the compressor will cut off faster, or you may not be switching on the equipment. So that is the, if you want to know about the reality of the energy consumption, so you have to be in touch with this cooling degree day and heating degree day. Okay, okay. So okay, fine. So now we are doing the energy simulation. Okay, energy simulation for throughout the year. Okay, so you can while doing the energy simulation, you can go for parametric studies. So usually when parametric study for improving the performance or improving the performance of the building. So when we will be going for a parametric study, so we will be, if we are having 1 or 2 parameters, okay, mostly in the buildings, 2 things we will be interested. You want to improve the comfort and you want to improve the comfort and decrease the energy cost. 2 things only will be doing: decreasing the energy cost, improve the comfort, or you decrease the energy cost, decrease the discomfort. Both you decrease the energy cost and decrease them. So for these 2 things, you can change the parameters. So what are the parameters you can change? You can change the glass to window, glass to wall ratio. You can change the glass to wall ratio. That is one. You can change the cooling set point. You can change the heating set point. Okay, so like that you can change the parameters and you can do the parametric study to understand for this much amount of change, okay, in that parameter, how much is the energy reduction. So that is called parametric analysis. For example, throughout the year, you change the setting. So the setting can be at 20 degrees. For 20 degree settings, what is the energy consumption? For 25 degrees setting, what is the energy consumption? For 15 degree setting, what is the energy consumption? So you can draw the line. So from that you can understand. So if I have 15 degree settings, what will be the energy consumption? If I have 25 degree settings, what will be the energy consumption? If I have 27 degrees, what is the energy consumption? Naturally, you should know that at 27 degrees setting, the energy consumption will be lower. But what is the rate of decrease in the energy consumption with the change in this setting temperature? So that can be analyzed. Okay. So this is called parametric analysis. So one typical parametric study is given here. Okay, so here you can see that the energy consumption is given in the y-axis, and here you are having the window to wall ratio. Okay, window to wall ratio. So if I am having a 100% window to wall ratio, that means we're totally open. So that means my energy consumption is 125K, okay, kilowatt hour, okay, 125,000 kilowatt hour. Now what I am having, so I am reducing it by 80%. What is happening? Again, it is 122, okay, 122,000 kilowatt hour. Now if I am operating at 30, so it is 100, okay, 100, okay, 1 lakh kilowatt hour, 1 lakh kilowatt hour. So 10%, okay, it will be 93 kilowatt hour. So that, like that, similarly here also, by changing the set point, you can draw a graph like this. What is the energy reduction? That you can do it. Similarly, by changing the heating set point, cooling set point. Similarly, by adding insulation. Okay, so what is the parametric? So by reducing the outdoor air, by reducing the ventilation, percentage reduction in the ventilation, what is the energy? So all this parametric study, it is possible. Okay, so you can do it in the solve. Okay. And next you can go for optimization also. Okay, so in the design builder software, so there is an algorithm, okay, called as genetic algorithm, okay, where you will be doing optimization. Okay, so already I told you. So what will be our objectives? So whenever there is optimization, we should have objectives, design variable and constraints. So our objective is two. One is minimize the carbon emission. In other ways, minimize the cost, minimize the running cost. Minimize the running cost means the carbon emission will be smaller. Okay, reduce, it will reduce. And similarly, minimizing the construction cost. Okay, minimizing the construction cost. So minimizing energy and minimizing the first cause. That you can do it. Okay. Similarly, minimizing the carbon dioxide. Okay, minimize carbon dioxide inside that, and minimizing the discomfort. So that also you can say. So many objectives you can take it. Okay, just I'm mentioning what are all the objectives. So what are all the design variables? So just now I told you, window to wall ratio. It can be set point temperature, cooling set point temperature, heating set point temperature, ventilation set point temperature, quantity of the ventilation. Okay, so like that you can have different varieties of things. Okay, so uh, design variables. Okay, and you can add constraints. So what is the range of value for these values? Okay, so you cannot go below certain value. For example, room temperature you cannot go below 22 degrees. Okay, so like that you can have your add your constraints also. So that you can do it, and you can go for optimization. So for optimization, so it is inbuilt. Okay, so we have a genetic algorithm. So in the design builder solver, so for doing this optimization. Okay, so what is genetic algorithm? So it is based on the uh, it is based on that science. Okay, so a genetic concept. Okay, so if you are having, okay, so if you are having very good, okay, very good species. Okay, so that as the all the good characters, it will be getting collected, or you have to collect all the good characters. Okay, so and if you try, if you make it to reproduce, okay, then you will be creating the best possible individual or best possible result. So here instead of individual, you have to tell best possible results. Okay, so that is how we are doing. So first we are randomly generating the population or values. So what is their objective? You have to reduce the minimize the uh, energy consumption. We will take it, minimize the energy consumption, minimize the discomfort. So we will take these two things, and we are going for the optimization. So when I'm going for optimization, okay, so the first I'll be having first calculations what I am having. So those are all, it will be called as current generation values. So first I'll be starting here. Okay, and after that, after I start the calculations, so you know that where you have to head, you have to head towards here, because you want to minimize the carbon dioxide, you have to minimize the discomfort. Okay, so that means you should be both, it should become zero. Okay? But because of constraint it cannot become zero. Okay, it cannot become zero. So that means the best possible will be like a rectangular hyperbola. Okay, so rectangular hyperbola like this. Okay, so that means now you will be starting somewhere here. Your calculations will be starting somewhere here. So when you are starting, so you will be doing the calculation. So that means that 10 variables, you will be starting with the calculation, calculating these two, carbon dioxide and discomfort. So when you are calculating, first it is possible that you can go in this direction also. That means you can go in the direction of decreasing. Some values can go in the value of increasing carbon dioxide and increasing discomfort. So that means those are all not the correct individual. So those are the values to be discarded. So healthy individual are the best thing is it has to march towards this. It has to march towards it. That means it has to go in the direction of reducing discomfort. So you collect all those populations. Okay, in that you try to get the best possible. You make it to reproduce these values. You make it to reproduce. You try to get the best possible. So if you do like that, okay, so if you are somewhere here in this direction and all, you will reject. If you are going in opposite direction, you will reject. Then all the values it is coming in this direction. Okay, so you will calculate what are all the values coming very faster to this direction, you will get give the higher ranking. So that means those are all called as uh, current generation values. So that means the latest value. So you will only pick the best values which will be reaching this place. Okay, reaching the target. So all these values will be marching in this direction. So after final thing, okay, so you get the Pareto front. So that means this is the best possible value. Okay, beyond that you cannot go. So that means you are getting somewhere data from somewhere, you are starting the calculation. So you are finding if it is if the discomfort and the carbon dioxide is increasing, you drop all those values, and where it is increasing, you pick up all those things. You do clubbing and do again calculations. Like that you proceed. Finally, you will be getting it. Okay. After that, you pick this value. So that is the best possible. Right? So that means this optimization it is possible. And you can see what are all the parameters: window to wall ratio, heating set point, cooling set point, external windows, okay, mixed mode ventilation, okay, natural mode ventilation, okay. So all these things. So the variables we are going to govern, it is uh, carbon dioxide, okay. So the objective is reduction of carbon dioxide, reduction of discomfort, okay. So these are objective functions. So this is how using a genetic algorithm, okay. So that is how, okay. So the best possible is that what, so it should go towards reducing the discomfort and reducing the energy value. So then you pick that. So if it is best possible, you stop, okay, you stop this and you move out. When you come to this point, it will move out of the loop, okay. So that is how you will be having this system. So this system is there. You can do the optimization. You can get the best possible things. Using that, you can design the building. You can design the building. So that means you can have the optimal value of window to wall ratio, and you can set the heating set point, cooling set point, okay. So external window percentage. So that internal window percentage. Similarly, how much should be the natural ventilation, how much should be the mechanical ventilation. All these parameters you can optimize, and you can tell to the building owners. So these are all the parameters at which you operate for minimizing the discomfort and the carbon dioxide, or minimizing the energy cost and the discomfort, okay. So these facilities are available in the solver, okay. So that you can do it. So okay, so yeah, so I told that. Okay, so you have the Pareto front. So the Pareto front is this one. Okay, so that is the best possible. I think I have explained everything. So it is what is given here. Okay. Okay, so this is the things that, thank you. And the next one is the same thing I have done. Okay, so I have started with one calculation for here. So here you can see the values. It started somewhere here. Slowly it is marching towards this point. Okay, and I have stopped somewhere in between. Okay, so that's why it's stopping here, because it was running for a very long time. So like that, you can make it to proceed. Okay, and you can do the things. So here you will be having optimal values. Okay, so it will give us the optimal value. So the best possible value you can select. On that, what are all the various parameters that you have to select? See here, for example, if it is telling the optimal value of window to wall ratio is 20, then you have to make it to 20. Similarly, setting heating set point, if it is telling 20, cooling set point, if it is telling 24.3, so you have to select those things. Okay, so that is how we have to do it. Okay, so that's what here you can see in the analysis. You have analysis, you have the summary. Okay, and you have parametric study, you have optimization, okay, data visualization also is there, and the summary. Okay, so you can see the summary. Okay, so here you can see summary is like your Excel sheet. Okay, so what is the report it is giving after completion. Okay, so here you can see I did it for interlow conditions. So this is how I am getting the report. So the energy consumption, it will give what is the energy per meter, kilowatt per meter square, energy condition building per meter square, and what is the consumption for cooling or heating. Okay, so all these values will be there here. Okay, so that is how. Okay, so that is how you can have different values. Okay, so I have some whatever the simulations you are doing. So for that you can have different values for this is somewhat for 24 hours operation. That's why you will be having heating and cooling. So I told you, no, I had a doubt. I worked for 24 hours. So that is how AMAT. If I go for 24 hours, then I have heating and cooling. Okay, so AMAT, if it is if you don't have that 24 hours, okay. So here you can see this value will be higher. So distinct heating values. If you are having daytime alone, the value is smaller. So that is what you have to see. So a lot of simulations you can do it. Okay, it will be very interesting. Okay, so I have done for Barcelona. Okay, Bintulu, Chennai, so Delhi. Okay, so all these things we can do it. Okay, can give the values and then you can get a comprehensive thing. Just for simulation, I have taken this. So that's why it is given like this here. Okay, so thank you. So now, if any question is there, I can answer. Okay, thank you. You can put your questions in the chat box. Yeah. Any question is there? How to determine the compressor run time for a year? Okay. So whatever the heat load you are calculating or the cooling load, whatever you are calculating, so a pro rata to that only compressor will be running. For example, during the peak day, compressor will be running for a long time because it was designed for that one day only. No, so it will there the compressor will be running for a very long time. Okay, if it is coldest day, okay, the compressor will be running for a shorter time. Oppositely, if it is a heater, in the coldest day, night time, it will be running for a very long time. And if during summer time, it will not at all running. So that is how, okay. So this heating load or the energy, okay, energy, whatever you are calculating, so that will give you what will be the compressor running time. For example, here itself, I will show you. So here you will see during this time, okay, so during this time the compressor will be running for a very long time because peak load, long time. And if your cooling equipment is working in these days, that means load is very much lesser. So in these days, the compressor will be running for a shorter time. In fact, if it is cold, okay, your heater will be working. Okay. So the rule of thumb is whenever your load, external load or ambient temperature is higher, solar radiation is higher. So that point, or sometimes internal load also may be higher. So if whenever your load is higher, your compressor will be running for a longer time. Whenever your load is lesser, the compressor will be running for a shorter time. Okay. Yeah. Why room electricity curve in the graph shown from the design builder results in always constant for all around the year? Room electricity is because of lighting. Okay, so it is not because of if it is because of cooling, so then it will increase. You are finding that for cooling it is increasing and decreasing. But if it is for lighting and fan and other equipments, for example, computer and other things, so it will be mostly constant throughout the day. And you are giving that. Okay, so you are telling that it is an office building. It will be working from 8 o'clock to morning 8 o'clock to evening 6 o'clock or 5 o'clock. So you are giving the value. So from 8 o'clock to 6 o'clock, your computer will be working continuously. Your fan will be working continuously. Light will be working continuously. So it is that you are giving. So that's why in the simulation it is showing like that. But in reality it is not so. But if you are going out, you will switch off your fan and you will. If you are going out for a coffee, okay, so you will switch off your fan and then you will go. Sometimes you switch off your light and then you may go out. If you are going for a site, okay, you may switch off the light and even AC also you may switch off and then. So in reality, that is different. While doing the load calculations, you are giving like that. So that is why it is coming it as constant. Okay. Hope that explains. Yeah. Any other question is there? But electricity curve for cooling, it will be varying. Okay. So just now I told you. So if it is a if it is a summer condition, so the energy will be higher. Okay. If it is winter condition, the energy will be smaller. Or in other words, compressor cutting time will be lesser during winter, and the cutting time will be longer. Or compressor working time will be longer during summer. I think I explained the questions. Okay, I think hope today's session was useful for you. If there is no more questions, then we can wind up today's discussion. Thank you for joining. So tomorrow we will have a discussion on phase change integration in building. Okay. So along with that, I am going to discuss about the building heat transfer also. Okay, building heat transfer or wall heat transfer also. How the wall heat transfer to be analyzed. Okay, how wall heat transfer to be analyzed in a building. So that concept also we are going to discuss tomorrow. Okay. So thank you everyone. Thank you for joining. Thank you.